Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, our topic are the different kinds of collisions. We looked at momentum, we looked at impulse, we looked at the conservation of momentum, and today we're going to finish off by looking at the different kinds of collisions there are. And so to put it out there, I wanted to just begin with a question, and I want you to think about it. If you think about all the collisions there are in our universe, what are the different kinds? I mean, this question I kind of already alluded to. There are different kinds of collisions, but how would you describe or distinguish between the different collisions in this universe? That's what we're going to take a look at today. And so let's jump into it. The first type of collision that we have is what we call perfectly inelastic collision. Elastic means stretchy or think of a bouncy ball, okay? A toy bouncy ball or a rubber band. They're very elastic. They bounce off of one another. So if we have a inelastic collision, we have a collision in which they don't bounce off of each other, or in other words, two things stick together. So if I have two carts that are both going to the right, and one is going faster than the other. I have this is my first cart that has a certain amount of momentum. This is my second cart that has a certain kind of type of momentum. Eventually, since this one's moving faster, it's going to collide with this and stick together until it reaches the end of this ramp here. And so our equation for that, if you notice, is the first equation in your stick together perfectly inelastic equations. Our masses will be added together and they'll be moving at the same velocity. Okay, that's what we call a perfectly inelastic equation. And so, for one example of that, let's say we have a luxury sedan and a stop at a traffic light, and for some reason there's a guy in a compact car not paying attention because he's on Instagram, and he rear ends that first luxury sedan. That's 1,850 kilograms. Second car is 975 kilograms, and they become entangled. The car eventually has a initial velocity at 22 meters per second. What is the velocity of the final velocity of the two cars? Yeah, so if we plug in our numbers, notice that first sedan, that's this amount of mass, was at rest, and so its velocity is 0 meters per second. And the second car is going at 22 meters per second. Eventually they collide, so their masses combine, and we have a final velocity there. So if we calculate for that, we would get our final velocity about 6 meters per second to the north, 7.59 to the north. And so here's the interesting thing about our perfectly inelastic collisions. When we talk about conservation of energy, whenever we have a inelastic collision, kinetic energy is not conserved. Some of it will be lost because of the heat, sound, or other energy types as mentioned here. And so when we have the change in kinetic energy for inelastic collision, it will not be equal to 0. Okay, we're gonna get some number here, and that's another way you can figure out that it is an inelastic collision. If you plug our numbers into this equation, our mass or velocities, and it comes out to a number that there is a change in kinetic energy somewhere in the problem, then we can conclude that it is an inelastic collision. And so here's an example of that. Let's say we have two clay balls that collide, and the first ball has this kind of mass, 0.5. Initial velocity of 4 meters per second to the right, positive. Second ball has a mass of 0.25 kilograms, initial velocity of negative 3 meters per second to the left. And we want to find the decrease in kinetic energy. So right away, you should know that it's going to be an elastic collision because there's going to be a decrease. It's not going to be 0. So if we set up our equation, our change in kinetic energy, or delta KE, is final minus initial, or remember that kinetic energy is mass times velocity. And so notice here, this is the first and second clay ball, and eventually they stick together, and so we can add them together. Final values minus initial values. So if we plug in our numbers here, and sorry it doesn't all fit on one line, let's continue down here. But we find that our final velocity, we don't really know what our final velocity is when they stick together. And so because of that, we can't actually figure out our change in KE because we have two unknown variables. And so what we're going to have to do, this is a two-step problem, we're going to have to find that final velocity first using what we figured out from the last problem. if we take our impulse equation, mvi when mvi2 equals our final masses combined plus our final velocity, we can figure out what that final velocity is. And so let's plug in the numbers. We have 0.5 times 4, 0.25 times -3, that's the second ball. And then they stick together, so we combine their masses, and they're gonna be moving at the same velocity, the same final velocity. So we come out, if you calculate it, you can check my work, it comes out to 1.67, which now we can plug it into the original equation. And so notice I substituted it right here. Don't forget to square the velocities. And eventually you would find that your kinetic energy, and so notice this is our final minus initial, that's why I have a parentheses around the last two, the 4 and the -1.125, that's our initial and our final. Okay, I have to do the parentheses first, and I would get a -1.83 joules. So notice the decrease in kinetic energy in this collision would be -1.83 joules. Okay, so that's how you would figure out the change in kinetic energy for a inelastic collision. The other type of collision we have, if we have inelastic, we also have elastic collisions. And so an elastic collision is where two things move away from each other after the collision. So let's say there's a little spring on a cart, they're both moving at each other and they collide, but because there's a spring, they move away from each other in opposite directions. So in this case, notice the only difference is that our masses are not combined and that we're going to have two different final velocities after this collision. And so in an elastic collision, kinetic energy is conserved, which means then that if we're to calculate for our kinetic energy would turn out to be 0. And so this only truly happens when we have atoms, electrons, protons, really small things colliding with each other in our universe. Yeah, so that's how those are the two different kinds of collisions and how to calculate for them, how to figure out if they are elastic or inelastic. Remember, it's the change in kinetic energy that kind of defines both. And so thank you so much for joining us, and we'll see you next time.